Hello, everybody. We're going to talk about the second half of lesson 3, which is Dalton's law of partial pressures. I want to start by showing you real quick in the simulation that we used where this comes from. So I'm going to go in here and hold the volume constant. I'm going to add some particles, and notice that these are two different types of particles. So I've got the heavy gas and the light gas. If I add some heavy gas, we're going to take a look at what the pressure comes out to. It's about 6, maybe 5.8, a little under 6. If I double the number of moles, or the number of particles, I would expect the pressure to double. When I do that, I get about double. And notice that I used the other types of molecules, and it didn't make a difference. I'm still at about 12, a little under 12. I can do that, keep going, mixing the different types. Again, it went up by around 6, a little under 6. It can go more heavy, a little under 6. So the relationship between the number of moles and the pressure is proportional. In other words, if I said there's 100 molecules of this heavy gas, then those 100 molecules, the pressure that they contribute to the total is exactly half, because they're exactly half the molecules. So looking in our equation here, P total is the total pressure of some container. So the total would be the total in the room, the total in a syringe, in the container, whatever it is. This comes from the pressure of some gas, so gas A, in our mixture, plus the pressure of some gas B in our mixture, plus the pressure of some gas C in our mixture, and I can go on and on. I can have as many gases in the mixture as I want, and I'm just adding what we call the partial pressures of each gas makes up the total. That's it. But there's a few ways we can use this. So we can also say, okay, if I know the total, and I want to know the partial pressure of one of the gases, of gas A, for example, I can do some math with this. The partial pressure of gas A would be the mole fraction of the gas. So how much of the total number of molecules does it make up? We call that X sub A, X with a little a. This is the mole fraction of A. Could also call that it's the percent. If you see percent, it's the same thing. It's just whatever that fraction is times the total. So there's a few different questions where we can use these. The first example, the total pressure of an oxygen argon helium gas mixture is 755 millimeters of mercury. If the partial pressure of argon is 174 millimeters of mercury and the partial pressure of helium is 389 millimeters of mercury, then the partial pressure of O2 is, okay, let's think. Do we know what P total is? Yes, we know it in two different ways. We know P total is right here, 755. We also know P total is this equation. So it is the partial pressure of O2 plus the partial pressure of argon plus the partial pressure of helium. So I'm thinking, okay, do I have any of these partial pressures? I have two of them. I have argons and I have heliums. So let me go and plug those in. I'm looking for PO2. I have 174 and 389. And then I'm just going to use some algebra. I want to subtract both of these. So PO2 equals 755 minus 174 minus 389. So that would equal 192 millimeters of mercury. So I could skip right to this step. So I can see I have the total and I have these two partials. Oh, I need to go and subtract each of them. And that would be the partial pressure of O2, PO2. So you can have a question where they're all added. You can have a question where I give you percents. The total pressure of an ideal gas is 2 atm. It is a mixture that's 20% oxygen and 80% nitrogen. So P total equals 2.0 atm. The question asks me for the partial pressure of each gas. So I want PO2 and I want PN2. To find those, well, I'm going to take the mole fraction. So PO2 equals, well, that's a percent. Let me change it to a fraction, 0.2 or a decimal, times P total, 2, 0.4. So this is 0.4 atm. PN2, I can do the exact same way, or I can do it another way. So to do the same way, 0.8 from 80%, times 2 ATM equals 1.6, 1.68 ATM. But also notice this is still true, right? If I add these up, I still get the total. So if I find this first one, 0.4, I don't really need to do this math because I can just say, oh, well, there's only two gases. If I subtract this partial pressure, I get the other partial pressure. And for this question, it wants both, so I need to make sure that I give both partial pressures. So you can see questions where we're going to use the formula where we add them, questions where I use the mole fraction with percents. The last one is where I use mole fractions with actual moles. What is the partial pressure of carbon dioxide in a container that holds 5 moles of carbon dioxide, 3 moles of nitrogen, and 1 mole of hydrogen, and has a total pressure of 1.05 atm? Let me label what I have. I have PT is 1.05 atm. I would like to know the partial pressure of CO2. Final answer. And I have the number of moles. So what I need to do is go and figure out what is the mole ratio of the CO2. Well, the mole ratio of CO2 is just going to be the part over the total. When I say the part, I mean carbon dioxide is 5 moles out of how many total? 5 moles of CO2 plus 3 moles of N2 plus 1 mole of H2. So that's equal to, well, all those moles are going to cancel. That's equal to 5/9, which is 0.56 or 556, however I want to round that. So to find PCO2, I'm going to take the mole fraction times P total. Put that in my calculator. I should get 0.5, let's see, sig figs. I'm given 3 here, so 583 ATM.